So, okay, so what we did is we just took the idea of importance sampling. So if you know importance sampling, if you knew it before, this must be really simple, right? You just took down the importance sampler and write it down for the state space model, unnormalized distribution of the state space model and your proposal. Okay, so how this all relates to particle filters? Obviously, you can see that we already started doing things with state space models, but this is very inefficient, right? So if you look at the algorithm, one step of this algorithm, this is, let's say, a naive importance sampler. If you look at this algorithm, every time you receive an observation, you have to do this all again, right? You have to sample the whole path, you have to compute the weights for the whole path, and then you have to compute your approximation anew, basically, even after receiving y t minus t plus 1, right? So obviously you don't want that. If you do this, like you're gonna have like all t iteration complexity, it's gonna be t squared eventually. It's gonna be not feasible. It's not gonna be feasible, right? So what we are going to do now, okay, can we actually build? So I'm going to do this a bit fast because this is sort of the motivation. Can I actually? So at any proposal, right? So I'm not even writing a specific proposal here. At any proposal, you have this sort of structure, right? So not that I'm not assuming anything here, no Markov process or anything like that. For any given proposal, you have this decomposition because any joint distribution. Let's write it QX0. Yes. So at any given with any given proposal, you have this structure, right? And then remember what was our weight expression. I'm going to rewrite it. So this expression, right? If I write that expression again, so my weights, let's stick to the original notation. My weights were defined like this. And then I wrote it as a ratio of unnormalized measure over the proposal. Now, I can use, just as remember we did the same trick with the Bayesian update, the update of the paths. We can do the same trick. We can write this down as using the properties of the unnormalized measure. So this is just decomposing like this, right? Again. And I can do the same trick I did before. I can write this down up to time t minus 1. And I can write down the last bits. So xt1 t minus 1. Right. Okay, so now you see this sort of a structure emerges here that you can actually compute these weights. So this is just basically the weights over the path, that is previous weights, right? So let's write down like this. Times, so you have some incremental weight. Did I introduce a notation for that? I actually did. So it's so I mean this is the same xt given qxt given 1. It's the same expression, and we can call this expression now just to have a simple notation. Well, hopefully simpler notation like this, right? So what is the idea here? The idea here is that because of the structure of the state.
Dennis,
yeah.
Just quickly. So how are you meaning to distinguish this from the W0T up in the top left corner? Is one meant to be lowercase and uppercase, or? So
this one and this one, you mean?
Yeah.
So using well, I mean, it's a small difference, but.
Okay, gotcha.
Right. So this is meant to be the weights for the entire path. So this one, sorry, I'm going to point. This is meant to be the entire path weights, and this is meant to be the weights at time t, right? Given an observation yt, right? So I'm going to even simplify this further. So this is just to see you that the normal idea. So even if you use so I did this, but this didn't give us anything different than what we had before. Why? Because if you look at because I didn't use any specific proposal, I just used the generic decomposition of the proposal. So there is no like special structure in it. You can see that I still have the same computational complexity. So now I can compute these weights and I can store them. I don't have to recompute them. And only thing I need to do at time t to update these weights is use the previous weights, multiply them with this, right? This second red term. But this is still very costly. Why? Because you see the dependencies to entire path, right? Even if I remove the observation dependence, I still have to keep the entire path and evaluate it and so on, right? So, okay, so what's the idea then? So the idea is, okay, then can we use this intelligent proposal? This is which is gonna give us a very nice, very nice structure. What we can do is we can use a Markov proposal, right? Obviously. So I assume that my proposal is designed so that I have no dependence. So I can write this as a multiplication over queues. Transition kernels now is the transition kernels of the proposal, and then if I do this now, I can have a very nice expression for the weights. So I am going to, again, in the interest of time, I don't know if I'm going to finish earlier because of this, but so I am writing the same expression as before, like as before, like this. Then I'm going to write the proposal, sorry, the transition kernel of the state, the likelihood of the state space model. Now here I just have the Markov chain, so Markov process or Markov transition kernel. Okay, you can see that now the new weights, now weight with this modification is sort of straightforward to compute, right? Because I don't have to keep the path, I don't have to evaluate the new path. If I want to compute a weight, it just depends on the latest observation and maybe on my previous estimate numerically, it's going to be, right? Okay, so let's do it then. So imagine that now, how would you do the, let's introduce now the sequential.
Sorry, we've got a question.
This might be a stupid question, but in terms of like actual implementation, can we assume that we can evaluate all of these functions?
Yes, so in the model, when you describe a state space model, you are usually given a clear transition kernel, which is xt given xt minus 1, and g, which is your likelihood, and then q, which is your proposal you choose. And these are all possible to evaluate functions. So there are special cases where, let's say, you have an intractable likelihood, for example. Maybe that's the question refers to. In that case, obviously, this doesn't apply anymore, and there are like specific SMC schemes for those kind of problems. But here, we typically assume that, yeah, we can evaluate all of these densities.
Yep.
So, sorry?
Just that it's like proper evaluation, not just up to a normalizing constant.
No. So these F and G are yeah, proper evaluation in Q as well, right? So all of these are exactly possible to evaluate, which is the algorithm actually. So sequential importance sampling. Right, so I'm going to just first introduce what is called SIS, which nobody uses, and I'll tell you the reason. So here I am again going to describe one-step update of the algorithm, right? Again, because why? If you can, so let's say if I have samples already drawn, and I know how to update this, so I probably have to have weights as well. Let's say if I have weights evaluated already, right? So these are weights evaluated with using this function. So here specifically, right? And I know how to update it to sequentially to this. This is my algorithm, right? So why I'm giving this one-step update again is it's the same as the base update. If you know how to do this, then you sample from prior and you go on and you know the whole algorithm. Okay, how would you do this? So this is simple. So it's already given by this recursion, right? So once you have samples from the past path and the past weights already computed, again, for time 0, this is just sampling from prior and computing this for the prior. What would you do? You would just update your weights numerically. So you will never multiply this way when you implement this. It's always in the log space, which is something Alicia is going to tell a lot to you about. But in theory, so the notation I used here actually is different. So I said 1 to t minus 1, which makes sense. 1 to t. So the way you update your current weights is you basically multiply. So you store this weight. So see the simplicity here is you just store this weights instead of evaluating the whole path but the function every time, right? You just have to store this weights and you compute the final weight. And final weight sorry, and then you normalize this obviously, but the final weight is given by this expression I typed above. So I'm going to now tell you where the xi's come from. So yt is a single observation, right? We don't have an index over yt because yt is a unique observation. You don't have obviously particle index on it. And obviously where xt is sampled from, xti is sampled from q, xt minus 1i for each I. So the algorithm basically is, again, so maybe it's better to keep it here. So the algorithm basically is the first sample, again, I'm going to give you the same structure. Now sample just the last sample from proposal, right? And then weight, compute weights is like the importance sampler and normalize these weights, right? So you get the normalized weights as basically the, let's say these are small w, and then you normalize the big w. Okay, so this is sequential importance sampling. So there is no resampling, right? So what happens with this algorithm is as you sample and wait and go on like this, you don't resample. What happens is the weights, because of this multiplication structure, because of the entirely the numerical procedure, you basically end up with one weight being 1 for one particle and the others being 0, right? So you essentially, it degenerates really fast, and this is called weight degeneracy, right? So if you, again, this is maybe Alice is going to mention, if you're an SIS, there is weight degeneracy. So there's something called path degeneracy. That's something different. Degeneracy, if I can have it. I'm not sure if it's correct. Anyway, okay. So what people did now, then they introduced sequential importance sampling. So now I'm going to write the same algorithm again, which hopefully should help with, you know, make you remember sequential importance sampling with resampling. Okay, is there any questions with the SIS? Because it's sort of, was it complicated? I appreciate it's a bit messy on the notes.
Seems to be all good.
Okay, so here to you know, repeat, the main gain of sequential importance sampling over importance sampling is you can just do this sequentially, which means like it's computationally very efficient, right? If you look at the computation of this weight, it only requires your previous particle for each particle. It only requires your current observation, and that's it, right? And again, the question is, you know, whether you can evaluate all of this, assuming that you can do, you have your transition kernel well-defined, and observation likelihood is well-defined, and proposal is your choice. So you, by design, you can evaluate it. If you did a good proposal, choose a good proposal. Actually, it's not always obvious that you want to choose a proposal that's explicit. This is another topic. This is basically purely an online algorithm, right? And what is this going to give you? So before moving on, because I think I have some time. So what is this going to give you eventually? It's kind of, I cannot fit this anyway. So if you do this sequential importance sampling, what did you do eventually? Let's clarify that. So you had some samples, right? And you had some weights, which I denoted like, let's see, like this, right? Normalized weights. So you obtain this, right? And you know how to obtain this. You sample from prior, you use the weight recursion I showed you, you keep multiplying new weights with the old weights, and you evaluate the incremental weight, what is this called, an incremental weight, this bit. And you got this. And what did you eventually obtain? You obtained an approximation of the posterior distribution, right? So you get an approximation to this, basically, in the form of a weighted sample, right? You got some weights, and you got some Dirac that's evaluated at t, dx0t. So So this solved the filtering problem, right? This solved the problem that we wanted to solve originally, but this solved it in a way that you don't have to sample the whole path and evaluate the weights every time. You actually do this sequentially. And every time you basically do this sampling, and here you compute your new weights, you basically get an update, based update of some sort, right? So so these are going to give you, so this bit gives you the approximation of the previous posterior distribution over the whole path, and all the entire procedure, sampling and weighting, is going to give you the posterior distribution at time t, right? So this is actually solving the filtering problem. This is how it relates to what we have introduced as filtering, right? Okay, if that's clear, then we can move on. Right. So the problem is this algorithm, as I told you, is if you run this naively, no other numerical modification, the weights will degenerate. And this is something you can do yourself to convince yourself in the practical. For example, just run this algorithm and see that actually weights converge to, they are quite degenerate. And it's quite simple to do. I mean, you can use a Gaussian model, for example, just as a model, or one of the examples in the notes. So now we can go now sequential importance sampling with resampling. So it's SI SR, that's what's called. So this is the same algorithm, right? So let's say again, we are given some samples. So this is, so there is some small details about how often you do resampling, like when you need to do resampling and when you don't have to do the resampling and so on. I am not going to deal with those, and I assume that we will do this step every iteration. But so okay, we are given these samples again, and we want to update our sample set, and probably we are not going to need weights, which I'm going to tell you why. Okay, so let's say you have these weights, right? What you do is you sample. So you have this sample set, right? What you do is you sample your latest. So let's again keep the structure. There is going to be sampling step. These are like 3 steps. Now, so you remember that the previous algorithm had 2 steps. You sample and you weight and you build your approximation, right? So now we are going to have 3 steps. We are going to introduce a step. So we sample from our proposal. Now we sample from Q conditioned on Q xt minus 1 for I equals 1 to n, right? And then I do now compute weights. Now let's assume that, so let's assume we compute weights. So in theory, we have to have previous weights, as I wrote above, and then we have the incremental weight, right? This is assuming that you have a weighted sample to begin with, but you may not have. That's what I'm going to clarify a bit. Okay, so what is the main difference between the sequential IS and this? People have introduced this resampling step here, right? So to make it 3-step algorithm purely, I mean, it has motivations. I'm going to tell you towards the end from like, algorithmic perspective. But in this case, at least if you look at from an importance sampling perspective, this is purely to resolve a numerical issue with the weight degeneracy. So if you do this, then you basically solve the weight degeneracy problem. What people do is people get, so let's denote this now as, because we will have 2 sets of particles. So I'm going to denote this X bar because now these are not my final particles yet because I'm doing resampling, right? So these you could call predictive particles. Why? Because this is sort of you move your state from xt minus 1 to xt. These are not your final updates, right? No, these are not your updated particles. And resampling, all it does is actually samples from this weighted distribution using the weights you have used. So I mean, this is like a
small question.
Yeah.
I must have missed one bit. Why is there a bar when you calculate the weights? It's f of x bar. What does the bar mean again?
It's the ones he's sampled. If you look one up.
Oh.
Yeah. So I introduced X bar. Now I introduce X bar because X bar. So now if you look at the previous algorithm, I didn't need X bar because when I sampled, this is all a mess, but when I sampled, if you look at here, or maybe I use the pointer better. If you look at here, I didn't use X bar because I sampled from this and I constructed my weights and I constructed my approximate measure. That's the next page. Now I'm introducing X bar because now the particles I will sample are not the final particles I will use, right? Because there's a resampling step. So now I had to distinguish particles before the resampling step and after the resampling step, which is an easy way to do this. These are sort of temporary particles, so I just use bar, right? So I sample from Q, and I have my X bars that are my sampled propagated particles using Q. Now I compute a weight associated to each of them, and the weighting recursion comes from the recursion I derived before, right? The sequential recursion. And then all this fancy step, this looks like a measure theoretic notation. All it does is it samples from this weighted, normalized weights. You sample indices from a multinomial distribution, and then you select the particles. So you just resample them, right? You just select the ones that you sample the indices, and you take the ones from your set. And this solves the problem of weight degeneracy, right? Well, in low dimensions, solves the problem of weight degeneracy. Right? And another thing I need to note is once you do resampling, you effectively set your previous or your weights to 1/n, right? Because you do resampling. Once you do resampling, your weights are not important anymore because you resampled with respect to those weights. Your new samples are unweighted set of samples from this weighted distribution. So if you were to do this, you can see that if you were to do this resampling at every iteration, in the next iteration, we wouldn't have this bit, right? This is why I wrote this in order to make the connection for the previous, algorithm. But normally, if you do resampling at every iteration, you actually don't have the first bit. You only compute the incremental weight, and you do this iteration, procedure again and again, right? So now, what happens if you resample sometimes and you don't do sometimes because it's not necessary every time? You basically do this weight. You keep these weights. Basically, if you don't do resampling, you keep storing your weights, right? If you do resampling, you set all of them to 1/n, which basically, in practice, you actually don't consider them at all. So you just compute incremental weights. If you don't do resampling, you keep like a history of your weights until the time you do resampling, right? And what people do usually, for example, they use something like an effective sample size. Again, this is going to be in one of the practicals to determine a time when it's good to resample. So because ideally in the algorithm the resampling introduces an error and so on, right? Okay, so this is sequential importance sampling with resampling. I'm not using still the particle filter word. This you could say this is a general particle filter in some sense. So I mean the most famous particle filter is bootstrap filter, which this is not the bootstrap filter yet, but this is sort of a general particle filter using a general proposal, right? Okay. Now I think we have every tool to.
We've got a question.
Yeah.
I think my question is kind of half-baked. I mean, I can see how clearly this does solve the weight degeneracy problem, right? Because instead of this exponential decay or growth of the weights, you just set them essentially to 1.
Mm-hmm.
It seems intuitively that you're also picking up additional stochasticity, right? Because obviously this result step is random. So does that extra variance show up somewhere? Yeah.
Well, I mean, in practice, it improves the performance. So there is no. So because sequential IS itself does seem to not work at all beyond like 10 iterations. So the comparison is not about the variance, but it just works versus doesn't work. But in theory, again, this is something Francesca will talk about. This introduces an explicit error. So it causes like a worse error bound, basically. So in theory, sequential IS is better than this. But apart from that, I think, so it does matter though how you do the resampling. So this is like an IID multinomial resampling, right? And there are better ways to do this. Like there are ways that you could do this more intelligently with lower variance. There you see the effect of it, I think I would say.
Yeah, there's also the link to what he said about only resampling some of the time. So it's sort of, if the weights are stable, then you don't want to resample
Yeah.
so much for the reasons you described.
As in, it's not the case that standard SAS is like the Rao Blackwellized version of SISR.
In a way, it is.
Yeah.
Because that would suggest the former should actually be better, right? But it's not better because clearly one works and the other doesn't.
I think you can't have a pure dominance result one way or the other, which Rao Blackwell would imply.
Okay, and is that basically because of the self-normalized nature or something like that? Both.
Kind of, yeah.
We can route vectorize one step. So if you do important sampling, when you do resampling, the approximation before resampling is better than the margins. But when you run a lot of them in sequence, you get this expected weight. One weight becomes one, which means you have low variance, but your bias is zero.
Yeah. Okay.
Well, there's the distinction between kind of Rao Blackwellizing at each time step versus over the whole bit. Right. I think you can go again if you like.
Right. Okay, so let's introduce finally the bootstrap filter, right? That was the whole point of the introduction. So the bootstrap filter. Okay. Well, let's go particle filter. Bootstrap particle filter. Okay, so okay, the bootstrap particle filter is really the most simple version of this you can think of, which is you can keep again the same ideas about sampling, resampling every time and so on, but you basically set your proposal to your transition canal, right? Why? Because I mean, if you think about it, so now I'm going to explain a bit why this algorithm makes sense. And so when people came up with this algorithm, they didn't think in these terms, right? They didn't derive it as an important sampler of path space and so on. They only thought about, how it would, how you could track a system. Mainly, if I'm not mistaken, it's usually coming from the electrical engineering literature, which is the people mainly were interested in tracking things, controlling things, and you maybe know that Kalman filter, extended Kalman filter, they were usually they were used in the Apollo moon landing, control of the space ship or space flight or whatever. And then people in 90s, when they came up with this nonlinear tracking, nonlinear systems, extension of the linear systems, they didn't think about in these terms. So that for them, it made sense if you were going to have an algorithm that is going to track something that you assume it's moving with respect to f, right? So here, let's write the algorithm and discuss some interpretations of it, right? Maybe I can, now that I'm ending this page, I can go to the other page. So again, the bootstrap. The bootstrap here with the cool O here. And okay, so what I was going to write, I was going to write sample. So sample, instead of now x bars sampled. So let's say again the standard story, we are given the particles of previous time, and now I'm not writing weights because I'm assuming that I'm resampling every time, so I'm not mentioning the previous weights. Now they're all set to 1/n. I'm sampling from my transition kernel now, right? Instead of a queue. Now, so you can see the weighting step getting actually quite simple. Why? So if we go back and look at the expression is you have f times g over q, right? And so f and q are the same, then they are going to cancel. So your weights are actually quite simple to compute. They are just your evaluations, but normalized. Let's say I am going to here again, sorry for the switching back and forth. Normalization is not written, right? It is normalized, all this stuff. So what normalization means, you just compute these weights here and then you normalize them to 1, right? They will be summed to 1. Okay, I am computing now my weights using just the likelihood for the sole reason that this cancels here, right? And then I have a resampling step. Resampling. So resampling is now I'm writing xt, wt, and I have my bar Yes. So again, here, just to do sampling from a multinomial distribution. So how we do it in practice, you sample the indices from this weighted distribution. You just select the indices you sample from this, right? So this is the bootstrap filter. And so now, I mean, I have like maybe 10 more minutes or so. I don't know if I will have time to introduce, but I will try to make this thing a bit more motivated. So how people thought about this, and maybe I introduce just a smoothing recursion, or maybe leave it to tomorrow. So why this was introduced and how people thought about this. If you think about the algorithm, so let's put this stuff to proper way. Okay, this is for okay. So so if you look back to the sort of intuition people had for this, and also I think Francesca will use a lot of the terms in her introduction to theories. She will use terms like selection, mutation, right? So how are these all related, and how people actually came up with this before considering it or understanding it as an important sampler? So you can basically see the intuition what people were thinking, right? So let's say I have an object that moves in space, right? So these are like, maybe I don't even need this complicated. So this moves like this, and this moves like this. And this would be the true xt minus 1, true xt, which I don't observe. If you assume at all it exists, is a philosophical issue, but you know, there is some system moves along space. And then you have, let's say, particles would be your estimate of the location of it, right? So each particle here, so let's say, I don't know how many I put here, xt minus 1I, it represents a cloud of particles over the state you are interested in, which is below xt minus 1, right? So now, why would people use transition kernel to actually move their particles? Because, you know, if the system is actually moving with respect to this blue curve, blue arrow, it makes sense to build your sampling step, or this is why it's called also prediction, right? Also, like, you can understand this in some sense approximating the predictive measure, which is one of the tools that you use in theory. What you would do is, in the first step of your algorithm, you would move your samples, right, towards where the system is moving, because that's what you think the system is doing, right, with some randomness if the system is stochastic, right? Now you have your predictive particles in red, right? And what happens is that, okay, let's assume that observation is just the noisy version of xt, right? It could be something very weird, or it could be some sensor in between nonlinear and so on. You know, the point of particle filter, these things are nonlinear. But assume that, let's say, it's just a noisy version of xt, so I have yt observed, right? So what I do now, I evaluate in the second step weight of each particle. So what does this mean? I'm evaluating each particle's probability or likelihood somehow in the second step. So what this means is, you can see that, for example, this guy is very far away from the yt. This will have a low weight because this is not explaining the observation very well. So its likelihood will be low. Like, let's say it's just a Gaussian likelihood. It's going to be log. This you think about log weights. It's going to be quadratic. So it's going to be pretty much the distance between yt and particle. So this is going to have low weight, and you can see that these guys are going to have very high weights because they are much closer to the observation, right? So what's going to happen is, I'm going to weight my particles as, you know, low weights and high weights, and I'm going to normalize the weight. So I have a set of unweighted particles, and I'm going to resample. Now, after I resample, probably I'll keep this, maybe I'll duplicate this, So I'll have a bunch of particles. Well, I mean, I'm not going to introduce new particles here, sorry. I have a bunch of particles that are selected from the red ones, now the blue ones, and some of the red ones are going to die, right? Because they have low weights, and maybe with small probabilities, you can select a bad particle as well. And then after resampling, you have a distribution now over xt, because now you use the information of the yt to basically, you know, in the weights and so on, and you build a posterior distribution over xt given yt incorporated, right? And then next step, you do the same. So you move your transition kernel with respect to, so you know particle with respect to your transition kernel, you compute weights, you resample, right? So this is why it's called also an evolutionary algorithm, and that's why it's called, some of the steps are called mutation and selection. So let's clarify that. So this is also called mutation. So if you look at this from an evolutionary perspective, right, and these two are selection. So why this would be the case? If you look at from an evolutionary perspective, what you're doing is, okay, you moving your particles. So you can think of these particles, you know, like a biology example. You can think of them as a member, as individuals, you know, belonging to a species. And in the first step, the algorithm does is that, now we are not thinking it as a tracking algorithm, but the algorithm does is you mutate, right? So things mutate over a lifetime, whatever, and then YT represents here the sort of the fitness landscape of the fitness landscape, let's say, the function. So YT gives you basically determines, oh, these particles are well fit to the environment, and these other particles are not, they are not a good fit because they are far away from the observation. And all the resampling, weighting and resampling together does is to select the new particles that are basically well fit, right? That were close to the observation, that explain observation well. So they basically, once you do weighting and resampling, you basically select the mutated particles. And that's also, you know, that's the reason why it's also called an evolutionary algorithm. So that's how people thought about it. But to recap, in a few minutes is that, so this is sort of an evolutionary algorithm, and this is sort of three-step algorithm that makes sense from an intuitive perspective. You obviously move your particles with respect to your transition kernel, and you weight them and so on. But eventually it could be understood as a much more general example of an important sampler over the path space. Depends on how you want to evolve your particles, right? You don't have to use the transition kernel. So what would be the appeal of not using a transition kernel then? Some of the discussion. I think I'm going to introduce smoothing tomorrow, hopefully. So what will be the use of other proposals, right? Sometimes you don't want to follow. So going back to the general case, right, rather than the bootstrap case. Sometimes there are a lot of motivation in the auxiliary particle filter case, for example. You may want to, I mean, maybe your observation is available already at this stage, right? Use my pointer. Yeah, maybe your observation is already available in this stage. So you don't want to do prediction. You know, you want to do a better update. You want actually your particles to be informed already to go to a better place. So you can embed your observation here, right? And you can sample particles in a way that they actually already are going to give you good weights, right? So the nice thing about having better weights here is that maybe it will reduce the need of resampling. Maybe it's going to give you more even weights. Maybe it's going to solve some of the degeneracy, right? Another area where you may need to use a proposal like this instead of using just a transition kernel is if you're really, really in high dimensions, right? And transition kernels, I mean, if you think about if you have thought about, you know, there's a lot of problems in the probability in high dimensions, but if you sample in a very high dimensional space from a transition kernel, there is no way that you can capture the meaningful mass you're interested in with a low number of particles, right? You need like exponential, the number of particles needs to increase exponentially with respect to dimension. But what you can do is you can use, again, maybe your observation, maybe something else you know about the system. Maybe you have a custom way to do this. You can use and plug this in here so that your particles are guaranteed to be in a region which is going to give you good weights, right? So this is mainly the main introduction of Q matters more about numerical issues, or also maybe your model is misspecified, for example. So you know F, but you want to actually introduce extra information in Q, so your particles end up in a different place. So all of this basically is the motivation of using a Q. That's not F, right? Okay, so this is the general particle filter. This is the bootstrap particle filter. And what I can do in the remaining time is first, so I'm going to, how many minutes do I have? 10 minutes or 15 minutes? So I was going to introduce smoothing, but.
Yeah, I think you can just keep going.
Yeah. So one thing I can mention is that for about.
Question.
Yeah. Yeah. Questions is a good time for questions. Please ask.
So the particles are the X subscript I right? And then you evolve them or something from a transition kernel, like to move them one step ahead in time, right? And then once you do the resampling step, and I'm thinking about like the middle bit in the graph you just in the picture you just drew, and when you do that, you basically resample the X size from the pool of X size that you have,
Yeah.
right? And some of them will be, present after the resampling, and some of them will be not present.
Yeah.
This is how you put them off. This is how it works. Okay.
So you will have duplicates, right? So for example, so if I take some risk and go to go to this notes. So these are the notes that I've sent you, right? So if you look at this picture, which is made my friend and he allowed me to use, which was nice. Sorry, yeah, here. So you can see, for example, here how the algorithm works. Right, this is a very famous figure. I mean, everybody uses this at some point. So you can see, for example, how the algorithm works. So you have some particles with weights before resampling. So I believe the first step. So again, do I have any pointer here? Probably not. So this first step is this denotes the particles with weights, right? And then you have the resampling step in between, but you can see that like particle with a big weight. Okay, resampling step here maybe. Particle with the big weight basically are retained, but then the others are killed, but you have duplicates in it, right? But so let's say this particle has basically 5 times duplicated from this particle with a big weight, right? So this particle was here 1 time, there is 2 duplicates here, there's 1 duplicate here, and so on. And then once you introduce some more mutation or propagation, you add, basically you get your 5 particles that are identical here. You introduce different noises to each of them, right? Because you use a transition kernel to propagate each of them. You draw a different random noise to add them in your transition kernel. So from the duplicates, you get like a very closely related 5 different particles, right? And from this is just 1, this just goes 1, this goes into 2 different particles in the mutation step or the sampling step, and this goes 1 and so on, right? And these particles are dead. They are never going to come back somehow. And then you do the same now. You get the likelihood. Likelihood is for fixed YT, right? There's just only unique 1 YT, and this is a function of X in many ways. So in many books or notations, you already can see that the likelihood is just denoted implicitly like this. So you don't even have a reference to YT, or people denote it like this or something. So YT defines a function, right? And you evaluate for each of your particles with respect to this function that's here. And these are basically, you normalize them and so on. These are going to give you new weight. So you see that the likelihood is high here for this particle. So you have a multimodal likelihood here, which is a nice example. So these particles in this region, they get high weights because the probability mass is higher here. And these particles here are going to get high weights as well because the probability mass is higher here. And it's the same story. There's 4 duplicates. This dies, there's 2 duplicates and so on, right? And then you just go on like this. So this is very
That's
like,
the one you did, so.
yeah.
So you just saying that's good?
I'm super happy. Thank you.
Okay.
All right.
We have another question.
Okay, fine.
I think it's gone around on an email this morning, but we can double check.
Yes, I sent it to who didn't get it. I don't know. I sent it to the list, the same list as Filippo's last email thread. I just changed one email that you suggested. But yeah, let me know. I mean, just send me an email. I can send it to. Okay. So I don't think I have time to introduce smoothing because it's already going to be 50 minutes in 5 minutes. I can mention a bit to basically set the stage for Francesca is because it's important to things are related. So here you can see that, for example, I can now, given these samples, right, my posterior predictive measure is is approximated. Now it's basically okay. So there are 2 choices. I believe also this is relevant. So one choice, you can use your weights and particles before resampling, right? So there are 2 ways of approximating your posterior measure here, and people, depending on what they like, they choose different things. One way is you do it at this stage. This stage, let's say this is 1, right? So if you want to approximate at this stage, let me call it a tilde approximation. These are going to be 2 different approximations. This is tilde because this is a weighted approximation. So you can use your weights from 1 to n, and you can use your particles that are bar, that are before resampling, right? So this is a weighted approximation using the samples coming from proposal or transition kernel in this case. So this is one approximation to the filtering distribution. Sorry. Given y1 to t, xt. So the second one would be after resampling. Obviously, it's the more obvious candidate maybe for people. Maybe I think I was. So let's denote t here. Whatever. I mean, this is. Basically, these indices are less important. You have to look what's inside the distribution to understand what the distribution is. And this is going to be now 1 over n, because these are now unweighted after resampling, right? That was the whole point. Unweighted samples. And these also approximates the same thing, right? So there are 2 different approximations, and they have, so in theory, you have more error in the second bit because, resampling effectively introduces error. And if you want to estimate the test function of like pi t phi, which is, for example, an integral of pi xt y1 to t, and a test function, let's say this is again an indicator function and so on, you basically build your estimators like using the, plugging just in here, whatever you like, right? You can plug 1 or 2, approximation 1 or approximation 2. You build your approximation. Let's say I'm using the unweighted one because it's easy to write. I'm writing like this, right? Okay, so what, for example, Francesca will do is she will basically derive bounds for this, estimators and the difference between this estimator and the original true estimator. And I believe she's going to do this LP bounds. And, these are going to depend on time and so on. And there's going to be some rate of convergence, right? And there's going to be a lot of discussion about, how resampling introduces error and so on. This is one thing. And so what I had something in mind, but I forgot. So what tomorrow I will do, okay, so there is going to be practical, right? For the tomorrow, the practical will basically introduce you to the computation of these weights because, these weights are never computed this way. So let's say you never actually compute f times g over q. You have to do everything in log space, and you do tricks in the log space to compute the weights in a stable way and so on. So these are going to be the topic of practical. So please, I would suggest you do it because this looks like an algorithm, right? But if you implement this in a naive way, it's not going to work. There are tricks. And one thing that I haven't explained to you is the problem of smoothing. So if you go back, that's more relevant to parameter estimation. So I'll try to do all of it tomorrow. Let's see how that goes. But so I introduced you to filtering, right? But what I haven't explained is building smoothers, which are distributions of this form, which are going to be tomorrow's topic again. xt given y1 to big T, right? So these distributions are different than filters because filters are small t here. I have big T. So what this distribution is, like given the whole observation sequence, you have seen everything, and you update. You go back and you update what you've seen. So once you see the future, it's easy to predict the past, right? It's that kind of thing. So you can build better approximations to your probability measures conditioned on the whole sequence y1 to t. And why this is important? And typically, if you want to fit a parameter, let's say you have parameters, right? You have to build this sort of distribution because sort of if you want to, let's say, do a maximum likelihood estimate or something else, you need to build you need to see the entire path and you build the entire smoother and so on. So this is what I'm going to tell you tomorrow. And I believe, I'm happy to discuss if there are questions, but for now, I think this is all I had for this morning, basically.
Cool. Any questions at this stage?
Just something to add on what we were discussing earlier about the 2 options that you have to estimate is exactly applying that probability. Option 2 is so option 1 is the conditional expectation of option 2.
Yeah.
And so in practice, usually you would prefer the one with weights because it has lower variance.
Mhm.
And so that's for one step though.
Yeah.
But if you have a lot of steps, then and you need option 2 in between all these steps to make it stay.
Yeah, so also one thing I haven't mentioned is different resampling ideas, right? I'm not going to describe them, but there are like stratified resampling, or there is systematic resampling, and so this one, it doesn't introduce bias. I mean, it introduces variance, but the other ones, they are actually biased as well. But in the interest of having lower variance, you have this bias variance trade-off, and they are sometimes used. I don't know how, like, fully practical implementations, but yeah. So the resampling, this is theoretically intuitive and understandable, but you don't have to do this. So.
Right. If we're good with questions for now, so next up is a short break and then the practical, basically.
Yeah.
So I guess if Dennis is done speaking for the moment, it makes sense to thank him.
Thanks a lot.
Okay.
Okay.
Yeah, a short break and then we'll get into
Yeah.
the practical.
Thank you. Thanks.
Thanks, Dennis.
Thanks. Bye-bye.